As we saw in the previous section in which we were solving linear systems, specifically by graphing, it was a great tool to be able to solve certain particular linear systems. So in this example right here, this red condition is the line that's graphed right there in the red, and then this blue condition right here is the line that's graphed right there in the blue. Sometimes when we graph lines, however, the coordinates that that are the intersection point are not necessarily the nicest of numbers. And so like in this particular case, I don't think exactly 0.571 is the exact. I think it just rounded it off, so I think there's a bunch more decimals, and the same thing right there. So if we actually wanted to find the exact solution for some linear system, sometimes graphing is not the best tool to give us the precise solution. So when we don't get necessarily the nicest like integer coordinates and that sort of a thing, we want to try to be able to tackle systems differently. And so we're going to do so algebraically, and specifically here we're going to use a method that's called the substitution method to do so. So a couple skills I just want to run through really quick, and then I'll run you through how the substitution method is going to ultimately be able to work. So whenever we're asked to deal with substitution in mathematics, right, it has to do a lot with substituting in like a sports sort of a context, right? So if we're asked to substitute b equals -2 into the expression -4b squared plus 1, then of course you just substitute in that value into the expression. So you just plug in the -2, right? And then you could, of course, go from there and simplify. So like you'd end up with -4 times +4 plus 1, which would be -16 plus 1, which would equal -17 as a result. But that's where the substitution happened, right? That's where we plugged in the -2. Or you could even substitute y equals 5 minus 3x into the expression 6y minus 10. So really, since y is equal to 5 minus 3x, they're the same thing, and we're going to substitute into here, we probably want to substitute for y. So it just becomes a matter of plugging in for y the fact that 5 minus 3x is the same thing as y. And then, of course, you could simplify. You end up getting 30 minus 18x upon distribution, and then you can combine your like terms. You end up getting that as a final result. But again, that's where the substitution was happening. And then whenever we're asked to solve something in mathematics, right, we're trying to find what that particular thing is that we're solving for, or to solve for it alone. So in this example right here, if we're trying to solve this, it's an equation for n, you just want to get the n isolated alone. So I guess if you subtracted 1 first, you end up getting that, and then you can go ahead and multiply by 4 then, and you end up getting a final result of n alone of -12. So that solves it for n. Here for x we're asked to solve, and we're solving this equation now for x, which means if I want to get this x alone, we'll probably want to subtract the y first, so that we get -2x is equal to -y plus 3, and then I guess we can take that side and divide by -2, and then divide everything there by -2. So we end up getting positive 1/2 y minus 3/2, and that solves that for x, which means that when we solve for x alone, we don't necessarily get like a number exactly for what x might be. It's just solving for x in terms of y and some other numbers. All right, so I've typed up steps that you could follow in terms of being able to solve by substitution. I'm not going to walk you through those, but you can go ahead and read through those later on if you want to. I'm just going to kind of give the steps as I go in terms of solving. So what we're going to do here is we're going to solve linear systems and use the substitution method to be able to do so. So we do have a system right here of two equations, and they are both linear equations right here. So the first thing that you're going to want to do when you are solving a system by substitution method is you first of all want to isolate a variable in one of the equations, or in other words, when we isolate a variable, you're solving for that variable. It does not matter if you isolate x, nor does it matter if you isolate y, just do so. And so we actually have this first equation right here, where actually you do have a y that's solved for, so we actually don't really need to do a lot of work right there, and we just kind of have that. So that's going to be your first step. And then this is where the fact that it's called the substitution method comes into play, is that now we actually want to now substitute into the other equation. So since we solved the first equation, this equation for a variable alone, we're going to substitute into the other equation. And the way this is going to work is that if we've now solved for the y alone, then you're going to substitute for y into the other equation. So what this will look like is we're going to take the other equation, which is 2x minus y, but now we're going to substitute in for y. And so since we want to subtract y, we want to subtract the entire thing. And so because we know that y was equal to negative 3x plus 5 from the other equation, we're going to put in negative 3x plus 5 where y was, because negative 3x plus 5 is what y is. Notice that I have the parentheses there. And then from there, once we've substituted into the other equation, and then you can solve for the value of one of the variables. And in this case, in this blue equation, we have an equation that only has x variables, so we actually can find a number value for what x is. So if we distribute that subtraction, we end up getting a plus of 3x, and then a subtraction of 5, and then we combine the like terms to get 5x minus 5 equals 35. So then there's a couple more steps. We can add 5 to both sides, which gives you 5x equals 40, and then you can divide by 5, which gives you then a value of x equals 8. So in order to solve this system, we not only want an x value, but we also want a corresponding y value that pairs with the x value to solve the system. So now as we go into step 3, now what we can do is we can substitute the variable value that we just found in step 2 into an equation to find the other variable's value. So in this case, we'll want to try to find the y value. So what that's going to look like then is, it doesn't matter which equation you pick, whether you pick that one or whether you pick that one, just pick one of them. So I'm just going to pick, let's say, the y equals negative 3x plus 5. So y equals negative 3, and then that's where I'm going to be able to plug in my known value of 8 that we just found, and then we should be able to find the y value. We're going to end up getting y equals negative 24 plus 5. That means that y equals negative 19 should be the corresponding y value. So we're basically done. Like your solution, I guess I'll write it up here. So your solution should be the ordered pair 8, negative 19. That should solve the system. And what you'll want to do to make sure that you know you've got the answer right is just a fourth and final step, is just to check your work and check to make sure that your x and y pair is going to satisfy both. So it turns out that actually we should know that it works in the first one. And the reason why we know is because that's the one we most recently used, where when we do plug in an 8, we know that we're going to get a negative 19 there. So that's just kind of an automatic. But what we haven't checked is we haven't checked plugging in both x and y into the other one. So that's kind of the only other thing we'll need to check to make sure. So if I take 2x minus y, I want to check to make sure that that's going to equal 35. So I want the 8 to go there because that was the x, and then I want the negative 19 to go there because that was the y. So 2 times 8 is going to give you 16, and then we do have a subtracting a negative, which is plus. And then 16 plus 19 does equal 35, so it checks out there as well. So therefore, because 8, negative 19 satisfies both conditions, then of course you know that that's going to be the correct solution to that particular system. Okay? All right, so now that breaks apart all of the steps. So now just some examples to really reinforce this. So if we're going to solve this by using the substitution method, then before you can do the substitution component, you need to isolate a variable alone. So when I take a look at the 2 different conditions right there, when I look at the second one right there, it's going to be pretty easy to isolate the x alone, but you want to have a positive 1x alone. So I'm going to take that equation, I'm going to add x to both sides, and what that gives me then is it gives me that x is equal to 2y. And so then now I can take that and I can substitute into the other equation. So I'm going to substitute in for x into the other equation now, but instead of x going right there into the other equation, so the other equation being 2x plus 6y equals negative 15, what's going to go there now is 2y, because we figured out from the second equation of the system there, that x is equal to 2y. So then, now what we get is we get 4y plus 6y equals negative 15, or 10y equals negative 15. And we're going to find a value for y now. So when we divide by 10, we actually get the fraction negative 3/2, which actually for this particular number, it's perfectly the decimal negative 1.5, so we could use that if we wanted to as well. So then at this point, now that we found y, your goal is just to find x. So you can plug in negative 1.5 into any of the two equations. Does not matter which one you plug into. So let's go ahead and how about plug into the second one. So let's say that 2 times y minus x is supposed to equal 0. So we're going to plug in the negative 1.5 that we just found for the y. So when you times those, you're going to get negative 3 minus x is equal to 0, and then we can solve this equation for x. So if we add 3 to both sides, then negative x is going to be 3, and then of course that means that x is actually negative 3. So let me circle that, so we know where we got our x and y values. So the last part of this is just to check to make sure that we're good. So we know, because we plugged in negative 1.5 into that second equation, that where I put that check mark, we're good there. So really we just need to check the first equation, what we haven't plugged both x and y into. So to check there, we want 2 times x plus 6 times y to equal negative 15. So your x is the negative 3 and the y is the negative 1.5. So if we multiply right there, you get negative 6. And if we multiply right there, you get negative 9. And we're going to add, and that does equal negative 15. So we're good there. So we have found the valid solution to this particular system. So the solution being the ordered pair, make sure you put the x first, negative 3, and the y, negative 1.5, gives you the correct solution to the system.